In the last video, this is where we stopped, and we did these 4 example problems together. Actually, the lower 3. And in the last 2, we focused on rings. And if you noticed, I kind of hesitated a little bit, right? We did these ring structures, and we just kind of flopped them out onto a sheet of paper. And the reason that we did the reaction is because it said, do SN2 and E2 conditions with them, and this is what will happen. All right, so the way that they worded the problem during that time allowed us some freedom where we could ensure that the reactions went forward. However, there's a problem. There is a problem with rings that we have to keep in mind. And in the last video, what you saw me do is we first started with a structure that looked like this up here at the very top. And I said, folks, this is not the only way we can draw a ring. We can draw a ring by looking down here at the very bottom. Okay, well, now what's going to be the issue here? What's he leading up to? What is this exception? What do I have to remember? And we talked about axial and we talked about equatorial bonds. Well, there's something to the story here that I need to tell you about. And what we need to remember when we do these elimination reactions is the concept of equatorial and axial. Back in the day, we said that chlorine, or really any type of group, is going to be more stable in the equatorial position. And folks, are actually so stable that E2 conditions with strong bases, not going to work. The molecule does not want to lose that halogen even though that it's ugly. It doesn't want to lose that halogen to create a double bond. You know, this ugly partner is with carbon, but it's not really giving it too many problems. It's in the right position. It's behaving itself. Carbon gets along with it perfectly fine. So what's the rush of getting rid of it? Now, if it's in the axial position, then it is slightly bothersome. That axial position is that chlorine is basically out on the street saying, hey, come and get me. Right here I am. And carbon doesn't quite like that. Carbon's going to go, oh, no. You don't want to do that. If so, when you keep that up, this is over. I'm ending it. So this chlorine is a bothersome, and carbon has to get rid of it. So the axial positions of the halogens, because remember we're talking about the halogen groups, are going to be less stable. Therefore, elimination reactions can happen with those. However, over here on the left-hand side, these halogens are basically, they're telling us, these are equatorial. And equatorial halogens on a ring system are so stable that elimination reactions do not happen. So I want to go back and take a look at this example problem. So the way the example problem was written, up here at the very top, you're seeing that. You're seeing that they really didn't tell us anything about axial or equatorial. The only thing they said was it had to be trans. So when we did this problem, up here at the very top, that's kind of how we started it. It didn't really matter which one was axial, which was equatorial, because they wanted you to show the elimination product. But they wanted us to assume that because elimination happened, then that chlorine had to be on an axial bond. But look at what I did here in the front. We went with this ring system, and I drew the ring with the chlorine on equatorial. Because we said this is the most stable. That's why we gravitated toward this. Well, if this was the case, folks, this elimination reaction actually would not happen. So we did a product. Over here, we drew this ring, we did a shaded wedge and another shaded wedge, and we said, there's your answer, there's your product, and then that's kind of how we left it. But I then did over here to the side another ring showing cis and trans. Notice this chlorine was pointed down, but it was equatorial. And then this chlorine here was pointed up, and that was axial. This substitution reaction, when that begins to happen, folks, that's what goes on there. But in the elimination reaction, when we start talking about cis and trans, no, we didn't really talk about elimination down here, and we didn't draw the sides of it, did we? This was only in substitution. So in the elimination reaction, we said this was the product, this ring structure with a double bond and a methyl group that was pointed out. It's still the product, but we're making an assumption. The assumption is that that halogen was in the axial position. If this carbon or chlorine was not in axial position and equatorial, we would not get an elimination reaction, and therefore there would be no elimination product from that reaction. So they wanted us to assume that's what we did. Notice I drew the side views of the cyclohexyls with the axial and equatorial bonds with the chlorines. That was for SN2's sake, not the elimination. I didn't really do that with the elimination, though. So in the back of our mind, we always have to keep that in mind. If the halogen is equatorial, no reaction happens. If it is axial, then a reaction can go forward. It does eliminate, and it does create a double bond. Right? Here's another example. Here we have a cyclohexane ring. We have a chloro that looks like it's equatorial, right? That's the most stable form. This methyl is equatorial. This isopropyl group here in the back, that is also equatorial right there. And I can see that slightly down, slightly up, slightly down, slightly up. And this will flip-flop back and forth. So we talked about ring flip. So all the equatorials can go to axials. All the axials can go to equatorial, not a problem. But if it's in this state here, there is no E2 that will go on. E2 only happens when these molecules have flipped and these halogens are now in the axial position. Those axial positions are saying, hey, come and get me. Right here I am. And those E2s then eliminate that chlorine. So that chlorine, pop, off it goes, and a double bond forms at that time. So just keep that in mind with some of the questions that they ask. Now, granted, I know ring flip happens back and forth, back and forth, back and forth, back and forth, but elimination is only going to go forward if these halogens are in the axial position. And a ring flip can fix that problem. But if they give me a structure like this and says, what's the elimination product, I'm going to assume that they want me to say no reaction because it's more stable. But if it flips and the halogen is now axial, an elimination reaction can go forward. All right, so we've talked about a mixture of different reactions now at this point. We've talked about SN2s, we've talked about SN1s, E2s and E1s. That's actually a mistake up here at the very top. So this needs to be SN1 and E1 and SN2 and E2. So SN1, E1s, we both said poor nucleophile. That's going to be the dead giveaway there. And SN2s and E2s, these are very strong nucleophiles. So these are fully blown negative nucleophiles. This nucleophile, sometimes I can put an H here, right, and get rid of that negative. So that means that it's not really fully negative. It's very weak. It's very unattractive. It gives carbon some time to be on his own or her own and then figure out where they want that carbocation to end up going. Stereochemistry-wise, again, very similar characteristics between the two halves of the reactions that we need to talk about. SN1 and E1, you're seeing both. Both E and Z's are formed. Both stereoisomers are formed, R and S's. Of course, the more stable one as far as E and Z goes, is going to be the major product, but you get major and minor products. So all of the possibilities exist there, folks. And then SN2 and E2. SN2, only the inverted product. It's got to go through the back door. R to S, S to R. As far as E2 is concerned, well, folks, it's still going to form a double bond. That double bond is still going to have EZ or cis and trans, and you still want them so that way the bulky groups are opposite of each other. So you still want the trans preferred or the E that's preferred in those products. So just the summary page, that's all that it is, nicely putting all four onto the same screen. We also need to talk about which one out of the routes. How do we determine what goes on? Well, I'm first going to tell you, and this is kind of what we've always done, we've divided them up into halves. We're first going to determine poor nucleophile or strong nucleophile. If they're poor, then SN1 and E1 are my possibilities. If they're strong, then SN2 and E2 are going to be the possibilities. And that's what this slide is basically telling you. That's a good way to sum up the information that's on here. This is something that we've done. It's something that we've looked at in every single example problem that we've done, and it's something that's not going to change in the world of substitution or elimination. Now we've got to go another step. And the next step is basically deciding, if we can, what goes on and how do we determine the difference once we break it up in the two halves. So, for example, let's say that only SN2 or E2 could go forward. So the question, only SN2? Only E2? Or do we get both? This is really one of the parts that a lot of people struggle with. You know, picking out that nucleophile is not that hard. Oh, there's a negative charge. That negative charge, please, that's easy. That's SN2 or E2. This is what most people get accustomed to, and that's perfectly fine. And if so, you've taken a right step. You're learning organic. The issue, though, is now that we've broken it down into the half, how do we determine whether the substitution route is preferred or whether the elimination route is preferred? Well, here's kind of the giveaway. Number one, if you have a very strong base, naturally, they are going to prefer the elimination product and not the substitution product. Which means that if SN2 and E2 are going forward, and I have to pick out a major product between these two, well, both are going to happen. But if I had to assign one of them the major product of the reaction, folks, E2 will get it almost every single time. SN2 happens, substitution goes on, that is a product. Elimination happens, double bond forms, that is a product. Out of the two, between SN2 and E2, because I'm using strong bases here, the elimination route will be preferred. Next, another trick that we can do to persuade it to do something is I need to increase the temperature. If I apply heat, if you see the triangle here, or you see the word heat, or you see the word hot in regards to the solvent, this is going to have you prefer the elimination product. So these are two ways that we can help distinguish between substitution and elimination. Again, both versions happen. Both versions are produced as a product. They both can be represented. But if I'm given the task to pick out the one in higher concentration or the one that's the favorite, the major product. It will be elimination anytime we use a strong base and anytime we increase the temperature. All right. So now we've got these reactions added into our bank. Our bank of alkene reactions, our bank of alkyne reactions, and now these eliminations and substitutions are going to go in. And all of this is going to be mushed together. Before I do that, though, I do want to talk about another type of elimination. Because I've just said that reactions of alkynes are going to be mushed in with elimination and substitution. So what you're seeing on the screen right now, look at this. This is NH2, Miss America. Miss America has walked into the bar, ladies and gentlemen, and she is there to take advantage of any carbon that she has her eyes set on. If you don't like that gender, just flip it. It works for male and female both. So this is very strong. Very strong nucleophile. Very strong nucleophile means an elimination is preferred. I know that now. And not only that, but E2 is going to happen. So NH2 is going to come in, and one round of NH2, folks, it would do what elimination is supposed to do. This NH2 is going to be like, ooh, yeah, I'm going to come in here and sneak and try to find me somebody to leave with tonight. And this carbon says, you know, guys, talking to the buddies, I'm in a relationship right now with 2 people, and I'm going to have to figure out what I need to do. 2 people, they're both ugly. They both are needy. I'm not attracted to them. It's a bad relationship. So I think that I'm going to maybe tell one of them at least to leave. And Miss America comes in, and Miss America comes over and says, hey. And then this carbon looks at that NH2 and says, yeah, that's the deal breaker. Bye-bye, bromine. And then at the same time, this carbon buddy is going to go slap, pew, and that NH2 is going to go away because that carbon is going to buy that NH2 a drink. That NH2 now turns into an NH3, and then off it goes. All right. So what we see is a double bond that gets formed. But look at this. That carbon is still in another relationship with another ugly thing that it's not attracted to anymore. And maybe that first Miss America left, but the second one comes in, and there's another one. And it does the same thing. I mean, if I was carbon, I would get tired of this stuff, right? So this NH2 comes in and says, hey, and then that carbon looks at that bromine and says, yeah, this is a reminder. It's not what I want. You got to go. Sorry. Pew. And then off that bromine goes. And then this carbon that's the neighbor again says, oh, no. This carbon just broke up. You need to give him some time. Pew. And off it goes. So that NH2 grabs another hydrogen to form an NH3. And what we form now is a triple bond. It's the formation of an alkyne. That's how we do that. So think about the alkyne reactions. We took a triple bond like this. We added HBr. H went on one side, Br went on the other. And then we added another round of HBr. And H went on the same side and Br went on to the other. And we would receive a product that would look like this. The 2 bromines would be on the same carbon. These are called geminal dibromides, so geminal twins. So think of this carbon as dating a set of twins. Both of them look exactly the same, and he's dating them or she's dating those twins at the same time. I mean, where's Maury Povich? That would be a perfect Maury show. That would be a perfect Jerry Springer show, wouldn't it? All this carbon, dating the twins, getting rid of one, Miss America's coming into the bar, all this soap opera drama. But that's what organic is. Down here at the bottom, well, we have a vicinal dichloride. So these are halogens that are on neighboring carbons. So let's take a look at what happens there. If I had a really strong base and I persuade elimination to happen, then the same thing's going to happen. This carbon's going to go, chlorine, it's just over. So, pink, off you go. So that chlorine is now freed up. And then this NH2 comes in, and the buddy says, no, NH2, you got to leave carbon alone. I'm sorry, but now's not the time. And then off NH2 goes to make NH3, and a double bond forms. All right, so when that double bond forms, well, the buddy also brought a date to the bar. And that buddy had a partner that was just as ugly. So now the time for that carbon to break up with their partner has came. So this carbon's going to look at that chlorine and say, listen, my friend just broke up with their partner, and I'm going to break up with you too. Maybe they're a source of inspiration, a support system. So that chlorine leaves. This carbon gets freed up. Another NH2 comes into the picture and comes in for the kill. And this buddy says, oh no, ponk, off you go. And we get a triple bond that's formed as well. So it happens either way. If the halogens are on the same carbon, then those halogens create the double and then the triple bond at that site. And if the halogens are side by side, they will gravitate together and they will form a double bond, and then they will gravitate again and they would form the triple bond. The question that I'll always get is, why does that triple bond form? So if the first formation, and let me do this number. Let me erase this double bond for just a second. Let's say a chlorine is here and a chlorine is there. So if the elimination reaction happens, this is always the question. So let's say elimination goes forward in round one. We get rid of the left-hand carbon and we create the double bond that's right there. Okay, that's great. A lot of people accept that fact. A lot of people can see that. That's perfectly okay. We can form the double bond on the other side, but if we do that, this is a CH2. This is more substituted than the other one. So that's why it gravitates to this position. So when the second round comes in, we're going to erase that chlorine and erase that bond. And some people will want to say, oh, look, there's a double bond already to the left, so I'm going to put a double bond here. It's not what it likes. This carbon, if it has a double bond to the left and a double bond to the right, that is accumulated diene. And those things are not very stable. Carbon doesn't just like to be in that position. The way to keep this in mind, this carbon has formed a stronger relationship to one of the friends. A bromance has occurred. Well, if that carbon forms another bromance with the other neighbor, then this carbon kind of spreads itself a little thinner. What tends to naturally happen is that if another bond is going to get formed, if the double is already there, even a stronger bromance is going to be taken between the two. And ladies, you better watch out, because that relationship can become so strong that they're now all about each other. Would you like to have a partner like that, who is maybe spending all their time with their best friend to the point at which you're questioning what are they really doing in their spare time? Well, that's what's happening with the alkyne world. So these two carbons are creating a stronger and stronger bond with each other. All right. So now that I've taken care of that, the concept that elimination can happen in more than one round. Sometimes they'll do it like this. You add a round of NH2, blah, 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 and then you add another round of NH2, blah, 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 blah. Or sometimes they'll just say 2 moles of NH2, or 2 moles of maybe OH. I mean, any strong nucleophile will work. This is the way they're going to represent that. So if one bromine can leave, folks, both of those bromines can leave. If one chlorine can leave, both of those chlorines will leave. It's just the idea of how much. How much of that nucleophile do you actually add into the bar, add into the club, in order to get those relationships to break up? That's what this is all about. Okay, so now we're here at the last leg of the lecture module, and we're also here at the last leg of the semester. So what I want to do now is kind of wrap up some of these ideas and topics together. And here we go. Here's our first one. So the question says, how do you make it? How do you make this? We really have to use little bits and pieces of everything that we've learned all semester, not just in this lecture module, in order to get to this point. So you might see this area here and you might say, hey, there's a double bond. That's an alkene. I know what alkene reactions are, so let's look at our alkene reactions and see how we can add on a C triple bond N. You can't. We didn't talk about that. However, what we did talk about, folks, is taking that double bond and reacting something like HCl to it, and look at what happens. That double bond breaks, two sites of attachment open up. Hydrogen goes on one. Maybe I'll write it down here just to make it match. And what went on the other? Chlorine. Ah, okay. This is one of the reasons that we talked about the addition of acids. Look at what it did. It put halogens onto an organic, and now I have an alkyl halide. And now we know these alkyl halides, well, we can do things with them, but we can also do substitution and eliminations with them, and we now know how to do that, don't we? So let's take a look at this chlorine, and if this chlorine could get substituted with this C triple bond N, then we're in business, folks. So can it? And the answer is yes, it can. How do we do that? Well, we add a really strong nucleophile N, so C triple bond N is the nitrile group, and a substitution reaction is going to happen. That chlorine will leave, off it goes, and in its place will be a carbon triple bond N, and we've just made our product here. So now we've taken these ideas that were scattered across weeks of lecture information, and we've tidied them up in together, and we've just added it into our assortment of reaction choices that we can do with these compounds now. So keep in mind, halogenate the organics, and substitution and elimination can prefer. Now, here's the kicker. Do I want to add in heat here? And the answer is no, not really. Because if I do a strong nucleophile with heat, then an elimination is going to get preferred. And that elimination is going to take the chlorine off, and it's going to reform the double bond, and we get back to what our starting reagent was. So that's something that we do not want. We do not want heat there at all. The other thing is that if we use a poor nucleophile, all right, so here we'll get rid of our negative, and we'll just add an H out in front. So that's a poor nucleophile. There's not a full-blown negative. A poor nucleophile will look at SN1 and E1 reactions. Once again, though, do not use heat. And this SN1 reaction can go in and still do what it needs to do. So that chlorine will end up leaving. A carbocation will form. This does not move. It stays in its position. There's no reason for it to move. Secondary, secondary, secondary. And this is where the incoming C triple bond N will go on to. So whether I use C triple bond N as a good nucleophile or HC triple bond N as a poor nucleophile, it doesn't really matter. It will give me the same product no matter which way I go with it. The issue, though, just make sure you don't use any heat, because that incorporation of heat is going to prefer a elimination reaction to go forward. So either one of those routes going to be perfectly okay. You do get byproducts. You will get a number of different byproducts here, right? We've talked about, even when we talk about stereochemistry, that's not represented in the problem, though. But there are different variants of products that I get, which is why a 60% yield is pretty good in organic. Look at all of these different choices that can happen. All right, here's another one. And this is where I'm going to stop the video. So I want you to write down this example problem, and I want you to tell me how you would make it. So you're starting reagents onto the left. It's an alkyl halide already, but they want you to make what's over on the right-hand side. Notice the halogen is gone, but we have an OH group. So see if you can figure this out. Use your rules of substitution, your rules of elimination, your rules of alkenes and alkynes, everything that you've learned up to this point. How can we get that OH group at that position and make it move away from that stationary tertiary carbon? It's a little bit more complicated than what it looks, especially in the very beginning at first glance. So see what you can come up with, and then press play on the next video and double check your answer.